The Pleuronectidae, or flatfish, are remarkable for their asymmetrical bodies. They rest on one side, in the greater number of species on the left, but in some on the right side, and occasionally reversed adult specimens occur. The lower or resting surface resembles at first sight the ventral surface of an ordinary fish. It is of white colour, less developed in many ways than on the upper side, with the lateral fins often of smaller size. But the eyes offer the most remarkable peculiarity, for they are both placed on the upper side of the head. During early youth, however, they stand opposite to each other, and the whole body is then symmetrical, with both sides equally coloured. Soon the eye proper to the lower side begins to glide slowly round the head to the upper side, but does not pass right through the skull, as was formerly thought to be the case. It is obvious that unless the lower eye did this travel round, it could not be used by the fish while lying in its habitual position on one side. The lower eye would also have been liable to be abraded by the sandy bottom. That the Pleuronectidae are remarkably adapted by their flattened and asymmetrical structure for their habits of life is manifest from several species, such as soles, flounder, etc., being excessively common. The chief advantages thus gained seem to be protection from their enemies, and facility for feeding on the ground. The different members, however, of the family present, as Schotte remarks, a long series of forms exhibiting a gradual transition from Hippoglossus pinguis, which does not in any considerable degree alter the shape in which it leaves the ovum, to the soles, which are entirely thrown off to one side. Mr. Mivart has taken up this case, and remarks that a sudden spontaneous transformation in the position of the eyes is hardly conceivable, in which I quite agree with him. He then adds, if the transit were gradual, then how such transit of one eye of a minute fraction of the journey toward the other side of the head could benefit the individual is indeed far from clear. It seems even that such an incipient transformation must rather have been injurious. But he might have found an answer to his objection in the excellent observations published in 1867 by Malm. The Pleuronectidae, while very young and still symmetrical, with their eyes standing on opposite sides of the head, cannot long retain a vertical position, owing to the excessive depth of their bodies, the small size of their lateral fins, and to their being destitute of a swim bladder. Hence, soon growing tired, they fall to the bottom on one side. While thus at rest, they often twist, as Malm observed, the lower eye upward, to see above them, and they do so vigorously that the eye is pressed hard against the upper part of the orbit. The forehead between the eyes consequently becomes, as could plainly be seen, temporarily contracted in breadth. On one occasion Malm saw a young fish raise and depress the lower eye through an angular distance of about 70 degrees. We should remember that the skull at this early age is cartilaginous and flexible, and so it readily yields to muscular action. It is also known with the higher animals, even after early youth, that the skull yields and is altered in shape if the skin or muscles be permanently contracted through diseases or some accident. With long-eared rabbits, if one ear flops forward and downward, its weight drags forward all the bones of the skull on the same side, of which I have given a figure. Malm states that the newly hatched young of perches, salmon, and several other symmetrical fishes have the habit of occasionally resting on one side at the bottom, and he has observed that they often then strain their lower eyes so as to look upward, and their skulls are thus rendered rather crooked. These fishes, however, are soon able to hold themselves in a vertical position, and no permanent effect is thus produced. With the Pleuronectidae, on the other hand, the older they grow, the more habitually they rest on one side, owing to the increasing flatness of their bodies, and a permanent effect is thus produced at the form of the head, and on the position of the eyes. Judging from analogy, the tendency to distortion would no doubt be increased through the principle of inheritance. Schiödte believes, in opposition to some other naturalists, that the Pleuronectidae are not quite symmetrical even in the embryo, and if this be so, we could understand how it is that certain species, while young, habitually fall over and rest on the left side, and other species on the right side. Malm adds, in confirmation of the above view, that the adult Trachypterus arcticus, which is not a member of the Pleuronectidae, rests on the left side at the bottom, and swims diagonally through the water, and this fish, of the two sides of its head, are said to be somewhat dissimilar. Our great authority on fishes, Dr. Günther, concludes his abstract of Malm's paper by remarking that the author gives a very simple explanation of the abnormal condition of the Pleuronectinoids. We thus see that the first stages of the transit of the eye from one side of the head to the other, which Mr. Mivart considers would be injurious, may be attributed to the habit, no doubt beneficial to the individual and to the species, of endeavouring to look upward with both eyes, while resting on one side at the bottom. We may also attribute to the inherited effects of use the fact of the mouth in several kinds of flatfish being bent toward the lower surface, with the jawbones stronger and more effective on this, the eyeless side of the head, than on the other, for the sake, as Dr. Tronquoyar supposes, of feeding with ease on the ground. Disuse, on the other hand, will account for less developed conditions of the whole inferior half of the body, including the lateral fins, though Yarrell thinks that the reduced size of these fins is advantageous to the fish, as there is so much less room for the action than with the larger fins above. Perhaps the lesser number of teeth, in the proportion of 4 to 7 in the upper halves of the two jaws of the Pliaceae, to 25 to 30 in the lower halves, may likewise be accounted for by disuse. From the colourless state of the ventral surface of many fishes, and from many other animals, we may reasonably suppose that the absence of colour in flatfish on the side, whether it be right or left, which is undermost, is due to the exclusion of light; but it cannot be supposed that the peculiar speckled appearance of the upper side of the sole is so like the sandy bed of the sea, or the power in some species, as recently shown by Pouchet, of changing their colour in accordance with the surrounding surface, or the presence of bony tubercles in the upper side of the turbot, are due to the action of the light. Here natural selection has probably come into play, as well as in adapting the general shape of the body of these fishes, and many other peculiarities, to their habits of life. We should keep in mind, as I have before insisted, that the inherited effects of the increased use of parts, and perhaps of their disuse, will be strengthened by natural selection; for all spontaneous variations in the right direction will be thus preserved, as will those individuals which inherit in the highest degree the effects of the increased beneficial use of any part. How much to attribute in each particular case to the effects of use, and how much to natural selection, it seems impossible to decide. I may give another instance of a structure which apparently owes its origin exclusively to use or habit. The extremity of the tail in some American monkeys has been converted into a wonderfully perfect prehensile organ, and serves as a fifth hand. A reviewer, who agrees with Mr. Mivart in every detail, remarks on this structure: "It is impossible to believe that in any number of ages the first slight incipient tendency to grasp could preserve the lives of the individuals possessing it, or favour their chance of having and of rearing offspring. But there is no necessity for any such belief. habit, and this almost implies that some benefit of great or small is thus derived, would in all probability suffice for the work. Brehm saw the young of an African monkey, Cercopithecus, clinging to the under surface of their mother by their hands, and at the same time they hooked their little tails round that of their mother. Professor Henslow kept in confinement some harvest mice, Mus mesorius, which do not possess a structurally prehensive tail, but he frequently observed that they curled their tails round the branches of a bush placed in the cage, and thus aided themselves in climbing. I have received an analogous account from Dr. Günther, who has seen a mouse thus suspend itself. If the harvest mouse had been more strictly arboreal, it would perhaps have had its tail rendered structurally prehensile, as is the case with some members of the same order. Why Cercopithecus, considering its habits while young, has not become thus provided, it would be difficult to say. It is, however, possible that the long tail of this monkey may be more of service to it as a balancing organ in making its prodigious leaps, than as a prehensile organ. The mammary glands are common to the whole class of mammals, and are indispensable for their existence. They must, therefore, have been developed at an extremely remote period, and we can know nothing positively about their manner of development. Mr. Minvard asks, is it conceivable that the young of any animal was ever saved from destruction by accidentally sucking a drop of scarcely nutritious fluid from an accidentally hypertrophied cutaneous gland of its mother? And even if one were so, what chance was there of the perpetuation of such a variation? But the case is not here put fairly. It is admitted by most evolutionists that mammals are descended from a marsupial form, and if so, the mammary glands will have at first developed within the marsupial sac. In the case of fish, Hippocampus, the eggs are hatched, and the young are reared for a time within a sac of this nature, and an American naturalist, Mr. Lockwood, believes from what he has seen of the development of the young that they are nourished by a secretion from the cutaneous glands of the sac. Now, with the early progenitors of mammals, almost before they deserve to be thus designated, is it not at least possible that the young might have been similarly nourished? And in this case, the individuals which secreted a fluid in some degree or manner the most nutritious, so as to partake of the nature of milk, would in the long run have reared a larger number of well-nourished offspring than would the individuals which secreted a poorer fluid, and thus the cutaneous glands, which are the homologues of the mammary glands, would have been improved or rendered more effective. It accords with the widely extended principle of specialization that the glands over a certain space of the sac should have become more highly developed than the remainder, and that they would then have formed a breast, but at first without a nipple, as we see in the Ornithorhynchus at the base of the mammalian series. Through what agency the glands over a certain space become more highly specialized than the others, I will not pretend to decide. Whether in part through compensation of growth, the effects of youth, or natural selection. The development of the mammary glands would have been of no service, and could not have been effected through natural selection, unless the young at the same time were able to partake of the secretion. There is no greater difficulty in understanding how young mammals have instinctively learned to suck the breast, than in understanding how unhatched chickens have learned to break the egg-shell by tapping against it with their specially adapted beaks, or how a few hours after leaving the shell they have learned to pick up grains of food. In such cases the most probable solution seems to be that the habit was at first acquired by practice at a more advanced age, and afterwards transmitted to the offspring at an earlier age. But the young kangaroo is said not to suck, only to cling to the nipple of its mother, who has the power of injecting milk into the mouth of her helpless half-formed offspring. On this head Mr. Mivart remarks, "Did no special provision exist? The young one must infallibly be choked up by the intrusion of the milk into the windpipe." But there is a special provision. The larynx is so elongated that it arises up into the posterior end of the nasal passage, and is thus enabled to give free entrance to the air for the lungs, while the milk passes harmlessly on each side of this elongated larynx, and so safely attains the gullet behind it. Mr. Mivart then asks, how did natural selection remove in the adult kangaroo, and in most other mammals, on the assumption that they are descended from a marsupial form, this at least perfectly innocent and harmless structure? It may be suggested in answer that the voice, which is certainly of high importance to many mammals, could hardly have been used with full force as long as the larynx entered the nasal passage, and Professor Flower has suggested to me that this structure would have greatly interfered with an animal swallowing solid food. We will now turn for a short space to the lower divisions of the animal kingdom. The Echinodermata, starfishes, sea urchins, etc., are furnished with remarkable organs called pedicellariae, which consist, when well developed, of a tridactyl forceps, that is, of one formed of 3 serrated arms, neatly fitting together and placed on the summit of a flexible stem moved by muscles. These forceps can seize and firmly hold of any object, and Alexander Agassiz has seen an echinus or sea urchin rapidly passing particles of excrement from forceps to forceps down certain lines of its body, in order that its shell should not be fouled. But there is no doubt that, besides removing dirt of all kinds, they subserve other functions, and one of these, apparently, is defence. With respect to these organs, Mr. Mivart, as on so many previous occasions, asks, what would be the utility of the first rudimentary beginnings of such structures, and how could such incipient buddings ever have preserved the life of a single echinus? He adds, not even the sudden development of the snapping action would have been beneficial without the freely movable stalk, nor could the latter have been efficient without the snapping jaws. Yet no minute, nearly indefinite variations could have simultaneously evolved these complex coordinations of structure. To deny this seems to do no less than to affirm a startling paradox. Paradoxical as this may appear to Mr. Mivart, tridactyl forcepses, immovably fixed at the base but capable of a snapping action, certainly do exist on some starfishes, and this is intelligible if they serve, at least in part, as a means of defence. Mr. Agassiz, to whose great kindness I am indebted for much information on the subject, informs me that there are other starfishes in which one of the 3 arms of the forceps is reduced to a support for the other 2, and again other genera in which the 3rd arm is completely lost. In Echinosis the shell is described by M. Perrier as bearing 2 kinds of pedicellariae, one resembling that of Echinus, and the other those of Spatangus, and in such cases are always interesting as affording the means of apparently sudden transitions through the abortion of one of the 2 states of an organ. With respect to the steps by which these curious organs have evolved, Mr. Agassiz infers from his own researches, and those of Mr. Müller, that both in starfishes and sea urchins the pedicellariae have undoubtedly been looked at as modified spines. This must be inferred from their manner of development in the individual, as well as from a long and perfect series of gradations in different species and genera, from simple granules to ordinary spines to perfect tridactyl pedicellariae. This gradation extends even to the manner in which ordinary spines and the pedicellariae, with their supporting calcareous rods, are articulated to the shell. In certain genera of starfishes, the very combinations needed to show that the pedicellariae are only modified branching spines may be found. Thus we have fixed spines with 3 equidistant, serrated, movable branches articulated too near their bases, and higher up on the same spine 3 other movable branches. Now when the latter arise from the summit of a spine, they form in fact a rude tridactyle pedicellary, and as such may be seen on the same spine together with the 3 lower branches. In this case the identity in nature between the arms of the pedicellary and the movable branches of a spine is unmistakable. It is generally admitted that the ordinary spines serve as a protection, and if so, there can be no reason to doubt that those furnished with serrated and movable branches likewise serve for the same purpose, and they would thus serve still more effectively as soon as by meeting together they acted as a prehensile or snapping apparatus. Thus every gradation from an ordinary fixed spine to a fixed pedicellary would be of service. In certain genera of starfishes, these organs, instead of being fixed or borne on an immovable support, are placed at the summit of a flexible and muscular, though short, stem, and in this case they probably subserve some additional function besides defence. In the sea urchins the steps can be followed by which a fixed spine becomes articulated to the shell, and is thus rendered movable. I wish I had space here to give a fuller abstract of Mr. Agassiz's interesting observations on the development of the pedicellary. All possible gradations, as he adds, may likewise be found between the pedicellary of the starfishes and the hooks of the ophiurians, another group of the echinodermata, and again between the pedicellary of sea urchins and the anchors of the holothuriae, also belonging to the same great class. Certain compound animals, or zoophytes as they have been termed, namely the polyzoa, are provided with curious organs called avicularia. These differ much in structure in the different species. In their most perfect condition they curiously resemble the head and beak of a vulture in miniature, seated on the neck and capable of movement, as is likewise the lower jaw or mandible. In one species observed by me, all the avicularia on the same branch often moved simultaneously backwards and forwards, with the lower jaw widely open, through an angle of about 90 degrees, in the course of 5 seconds, and their movement caused the whole polyzoary to tremble. When the jaws are touched with a needle, they seize it so firmly that the branch can thus be shaken. Mr. Mivart adduces this case, chiefly on account of the supposed difficulty of organs, namely the avicularia of the polyzoa and the pedicellary of the echinodermata, which he considers as essentially similar, having been developed through natural selection in widely distinct divisions of the animal kingdom. But as far as the structure is concerned, I can see no similarity between tridactyle pedicellary and avicularia. The latter resembles somewhat more closely the chelae or pincers of crustaceans, and Mr. Mivart might have adduced with equal appropriateness this resemblance as a special difficulty, or even their resemblance to the head and beak of a bird. The avicularia are believed by Mr. Busk, Dr. Smith, and Dr. Nietzsche, naturalists who have carefully studied this group, to be homologous with the zooids and their cells which composite the zoophyte, the movable lip or lid of the cell corresponding with the lower and movable mandible of the avicularium. Mr. Busk, however, does not know of any gradations now existing between a zooid and an avicularium. It is therefore impossible to conjecture by what serviceable gradations the one could have been converted into the other, but it by no means follows from this that such gradations have not existed. As the chelae of crustaceans resemble in some degree the avicularia of polyzoa, both serving as pincers, it may be worth while to show that with the former a long series of serviceable gradations still exists. In the first and simplest stage, the terminal segment of the limb shuts down either on the square summit of the broad penultimate segment, or against the whole side, and is thus enabled to catch hold of an object; but the limb still serves as an organ of locomotion. We next find one corner of the broad penultimate segment slightly prominent, sometimes furnished with irregular teeth, and against these the terminal segment shuts down; but an increase in the size of this projection, with its shape, as well as that of the terminal segment, slightly modified and improved, the pincers are rendered more and more perfect, until at last we have an instrument as efficient as the chellae of a lobster. And all these gradations can actually be traced. Besides the avicularia, the polyzoa possess curious organs called vibracula. These generally consist of long bristles, capable of movement and easily excited. In one species examined by me, the vibracula were slightly curved and serrated along the outer margin, and all of them on the same polyzoary often moved simultaneously, so that, acting like long oars, they swept a branch rapidly across the object glass of my microscope. When a branch was placed on the face, the vibracula became entangled, and they made violent efforts to free themselves. They are supposed to serve as a defence, and may be seen, as Mr. Busk remarks, to sweep slowly and carefully over the surface of the polyzoary, removing what might be noxious to the delicate inhabitants of the cells when their tentacula are protruded. The avicularia, like the vibracula, probably serve for defence, but they also catch and kill small living animals, which it is believed are afterwards swept by the currents within the reach of the tentacula of the zooids. Some species are provided with avicularia and vibracula, some with avicularia alone, and a few with vibracula alone. It is not easy to imagine two objects more widely different in appearance than a bristle or vibraculum and an avicularium like the head of a bird, yet they are almost certainly homologous, and have been developed from the same common source, namely a zooid with its cell. Hence we can understand how it is that these organs gradate in some cases, as I am informed by Mr. Busk, into each other. Thus, with the avicularia of some species of Lepralia, the movable mandible is so much produced, and is so like that of a bristle, that the presence of the upper or fixed beak alone serves to determine its avicularian nature. The vibracula may have been directly developed from the lips of the cells, without having passed through the avicularian stage; but it seems more probable that they have passed through this stage, as during the early stages of the transformation the other parts of the cell, with the included zooid, could hardly have disappeared at once. In many cases the vibracula have a grooved support at the base, which seems to represent the fixed beak, though this support in some species is quite absent. This view of the development of the vibracula, if trustworthy, is interesting, for supposing that all the species provided with avicularia had become extinct, no one with the most vivid imagination would ever have thought that the vibracula had originally existed as a part of an organ resembling a bird's head, or an irregular box or hood. It is interesting to see two such widely different organs developed from a common origin, and as the movable lip of the cell serves as a protection of the zooid, there is no difficulty in believing that all the gradations, by which the lip became converted first into the lower mandible of an avicularium, and then into an elongated bristle, likewise served as a protection in different ways and under different circumstances. In the vegetable kingdom, Mr. Mivart only alludes to two cases, namely, the structure of the flowers of orchids and the movements of climbing plants. With respect to the former, he says, the explanation of their origin is deemed thoroughly unsatisfactory, utterly insufficient to explain the incipient, infinitesimal beginnings of structures which are of utility only when they are considerably developed. As I have fully treated this subject in another work, I will here give only a few details, on one alone of the most striking peculiarities of the flowers of orchids, namely their pollinia. A pollinum, when highly developed, consists of a mass of pollen grains affixed to an elastic footstalk or caudicle, and this to a little mass of extremely viscid matter. The pollinia are by this means transported by insects from one flower to the stigma of another. In some orchids there is no caudicle to the pollen masses, and the grains are merely tied together by fine threads; but as these are not confined to orchids, they need not here be considered. Yet I may mention that at the base of the Orchidus series, in Cyberspatium, we can see how the threads were probably first developed. In other orchids the threads cohere at one end of the pollen masses, and this forms the first or nascent trace of a claudicle. This is the origin of the claudicle. Even when of considerable length and highly developed, we have good evidence in the aborted pollen grains, which can sometimes be detected embedded within the central and solid parts. With respect to the second chief peculiarity, namely the little mass of viscid matter attached to the end of the claudicle, a long series of gradations can be specified, each of plain service to the plant. In most flowers belonging to other orders, the stigma secretes a little viscid matter. Now, in certain orchids, similar viscid matter is secreted, but in much larger quantities, by one alone of the three stigmas; and this stigma, perhaps in consequence of the copious secretion, is rendered sterile. When an insect visits a flower of this kind, it rubs off some of the viscid matter, and thus at the same time drags away some of the pollen grains. From this simple condition, which differs but little from that of a multitude of common flowers, there are endless gradations, to species in which the pollen mass terminates in a very short free claudicle, to others in which the claudicle becomes firmly attached to the viscid matter, which the sterile stigmata itself much modified. In this latter case we have a pollinium in its most highly developed and perfect condition. He who will carefully examine the flowers of orchids for himself will not deny the existence of the above series of gradations, from a mass of pollen grains merely tied together by threads, with the stigmata differing but little from that of the ordinary flowers, to a highly complex pollinium, admirably adapted for transportal by insects. Nor will he deny that all the gradations in the several species are admirably adapted in relation to the general structure of each flower for its fertilisation by different insects. In this and almost every other case, the enquiry must be pushed further backwards, and it must be asked, how did the stigma of an ordinary flower become viscid? But as we do not know the full history of any one group of beings, it is as useless to ask as it is hopeless to attempt answering such questions. We will now turn to climbing plants. These can be arranged in a long series, from those which simply twine round a support, to those which I have called leaf climbers, and to those provided with tendrils. In these two latter cases the stems have generally, but not always, lost the power of twining, though they retain the power of revolving, which the tendrils likewise possess. The gradations from leaf climbers to tendril bearers are wonderfully close, and certain plants may be differently placed in either class. But in ascending the series from simple twiners to leaf climbers, an important quality is added, namely sensitiveness to a touch, by means of the footstalks of the leaves of the flowers; or these modified and converted into tendrils are excited to bend round and clasp the touching object. He who will read my memoir on these plants will, I think, admit that all the gradations in function and structure between simple twiners and tendril bearers are in each case beneficial in a high degree to the species. For instance, it is clearly a great advantage to a twining plant to become a leaf climber, and it is probable that every twiner which possessed leaves with long footstalks would have been developed into a leaf climber, if the footstalks had possessed in any slight degree the requisite sensitiveness to a touch. As twining is the simplest means of ascending a support, and forms the basis of our series, it may naturally be asked, how did plants acquire this power in an incipient degree, afterwards to be improved and increased through natural selection? The power of twining depends, firstly, on the stems while young being extremely flexible, but this is a character common to many plants which are not climbers; and secondly, on their continually bending to all points of the compass, one after another in succession in the same order. By this movement the stems are inclined to all sides, and are made to move round and round. As soon as the lower part of a stem strikes against any object and is stopped, the upper part still goes on bending and revolving, and thus necessarily twines round and up the support. The revolving movement ceases after the early growth of each shoot. As in many widely separated families of plants, single species and single genera possess the power of revolving, and have thus become twiners. They must have independently acquired it, and cannot have inherited it from a common progenitor. Hence I was led to predict that some slight tendency to a movement of this kind would be found to be far from uncommon with plants which did not climb, and that this had afforded the basis for natural selection to work on and improve. When I made this prediction, I knew of only one imperfect case, namely of the young flower peduncles of a Moraenda, which revolved slightly and irregularly, like the stems of twining plants, but without making any use of this habit. Soon afterwards Fritz Müller discovered that the young stems of Alissima and of a Linum, plants which do not climb and are widely separated in the natural system, revolved plainly, though irregularly, and he states that he has reason to suspect that this occurs with some other plants. These slight movements appear to be of no service to the plants in question. Anyhow, they are not of the least use in the way of climbing, which is the point that concerns us. Nevertheless, we can see that if the stems of these plants had been flexible, and if under the conditions to which they are exposed it had profited them to ascend to a height, then the habit of unsightly and irregularly revolving might have been increased and utilized through natural selection, until they had become converted into well-developed twining species. With respect to the sensitiveness of the footstalks of the leaves and flowers and of the tendrils, nearly the same remarks are applicable as in the case of the revolving movements of twining plants. As a vast number of species, belonging to widely distinct groups, are endowed with this kind of sensitiveness, it ought to be found in a nascent condition in many plants which have not become climbers. This is the case. I observed that the young flower peduncles of the above Moraenda curved themselves a little towards the side which was touched. Morin found in several species of oxalis that the leaves and their footstalks moved, especially after exposure to a hot sun, when they were gently and repeatedly touched, or when the plant was shaken. I repeated these observations on some other species of oxalis, with the same result. In some of them the movement was distinct, but was best seen in the young leaves. In others it was extremely slight. But it is a more important fact that, according to the high authority of Hofmeister, the young shoots and leaves of all plants move after being shaken, and with climbing plants it is, as we know, only during the early stages of growth that the footstalks and tendrils are sensitive. It is scarcely possible that the above slight movements, due to a touch or shake in the young and growing organs of plants, can be of any functional importance to them. But plants possess, in obedience to various stimuli, powers of movement which are of manifest importance to them. For instance, towards, and more rarely from the light, in opposition to, and more rarely in the direction of, the attraction of gravity, when the nerves and muscles of an animal are excited by galvanism, or by the absorption of strychnine, the consequent movements may be called an incidental result, for the nerves and muscles have not been rendered specially sensitive to these stimuli. So with plants it appears that, from having the power of movement in obedience to certain stimuli, they are excited in an incidental manner by a touch or by being shaken. Hence there is no great difficulty in admitting that, in the case of leaf climbers and tendril bearers, it is this tendency which has been taken advantage of and increased through natural selection. It is, however, probable, from reasons which I have assigned in my memoir, that this will have occurred only with plants which had already acquired the power of revolving, and had thus become twiners. I have already endeavoured to explain how plants become twiners, namely by the increase of a tendency to slight and irregular revolving movements, which were at first of no use to them. This movement, as well as that due to a touch or a shake being the incidental result of the power of moving, gained for other and beneficial purposes. Whether, during the gradual development of climbing plants, natural selection has been aided by the inherent effects of use, I will not pretend to decide. But we know that certain periodical movements, for instance the so-called sleep of plants, are governed by habit. I have now considered enough, perhaps more than enough, of the cases selected with care by a skilful naturalist, to prove that natural selection is incompetent to account for the incipient changes of useful structures, and I have shown, as I hope, that there is no great difficulty on this head. A good opportunity has thus been afforded for enlarging a little on gradations of structure, often associated with strange functions, an important subject which was not treated at sufficient length in former editions of this work. I will now briefly recapitulate the foregoing cases. With the giraffe, the continued preservation of the individuals of some extinct high-reaching ruminant, which had the longest necks, legs, etc., and could browse a little above the average height, and the continued destruction of those who could not browse so high, would have sufficed for the production of this remarkable quadruped. But the prolonged use of all the parts, together with inheritance, will have aided in an important manner in their co-ordination. With the many insects which imitate various objects, there is no improbability in the belief that an accidental resemblance to some common object was in each case the foundation for the preservation of slight variations which made the resemblance at all closer, and this will have been carried on as long as the insect continued to vary, and as long as a more and more perfect resemblance led to its escape from sharp-sighted enemies. In certain species of whales there is a tendency to the formation of irregular little points of horn on the palate, and it seems to be quite within the scope of natural selection to preserve all favourable variations, until the points were converted first into lamellated knobs or teeth, like those on the beak of a goose, then into short lamellae, like those of the domestic ducks, and then into lamellae as perfect as those of the shoveler duck, and finally into the gigantic plates of baleen, as in the mouth of the Greenland whale. In the family of these ducks, the lamellae are first used as teeth, then partly as teeth, and partly as a sifting apparatus, and at last almost exclusively for this latter purpose. With such structures as the above lamellae of horn or whalebone, habit or use can have done little or nothing, as far as we can judge, toward their development. On the other hand, the transportal of the lower eye of a flatfish to the upper side of the head, and the formation of a prehensile tail, may be attributed almost wholly to continued use, together with inheritance. With respect to the mammae of the higher animals, the most probable conjecture is that primordially the cutaneous glands over the whole surface of the marsupial sac secreted a nutritious fluid, and that these glands were improved in function through natural selection, and concentrated into a confined area, in which case they would have formed a mamma. There is no more difficulty in understanding how the branched spines of some ancient echinoderm, which served as a defence, became developed through natural selection into tridactyle pediculae, than in understanding the development of the pincers of crustaceans, through slight serviceable modifications in the ultimate and penultimate segments of a limb, which was at first used solely for locomotion. In the avicularia and vibracula of the Polyzoa we have organs widely different in appearance, developed from the same source; and with the vibracula we can understand how the successive gradations might have been of service. With the pollinia of orchids, the threads which originally served to tie together the pollen grains can be traced cohering into cauticles, and these steps can likewise be followed by which viscid matter, such as that secreted by the stigmas of ordinary flowers, and still subserving nearly but not quite the same purpose, became attached to the free ends of the cauticles, all these gradations being of manifest benefit to the plants in question. With respect to climbing plants, I need not repeat what has been so lately said. It has often been asked, if natural selection be so potent, why has not this or that structure been gained by certain species, to which it would apparently have been advantageous? But it is unreasonable to expect a precise answer to such questions, considering our ignorance of the past history of each species, and of the conditions which at the present day determine its numbers and range. In most cases only general reasons, but in some few cases special reasons can be assigned. Thus, to adapt a species to new habits of life, many co-ordinated modifications are almost indispensable, and it may often have happened that the requisite parts did not vary in the right manner or to the right degree. Many species must have been prevented from increasing in numbers through destructive agencies which stood in no relation to certain structures, which we imagine would have been gained through natural selection from appearing to us advantageous to the species. In this case, as the struggle for life did not depend on such structures, they could not have been acquired through natural selection. In many cases, complex and long-enduring conditions, often of a peculiar nature, are necessary for the development of a structure, and the requisite conditions may seldom have concurred. The belief that any given structure, which we think, often erroneously, would have been beneficial to a species, would have been gained under all circumstances through natural selection. It is opposed to what we can understand of its manner of action. Mr. Mivart does not deny that natural selection has effected something, but he considers it as demonstrably insufficient to account for the phenomenon which I explain by its agency. His chief arguments have now been considered, and the others will hereafter be considered. They seem to me to partake little of the character of demonstration, and to have little weight in comparison with those in favour of the power of natural selection, aided by the other agencies often specified. I am bound to add that some of the facts and arguments here used by me have been advanced for the same purpose in an able article lately published in the Medical Chirurgical Review. At the present day almost all naturalists admit evolution under some form. Mr. Mivart believes that species change through an internal force or tendency about which it is not pretended that anything is known. That species have a capacity for change will be admitted by all evolutionists, but there is no need, as it seems to me, to invoke any internal force beyond the tendency to ordinary variability, which through the aid of selection by man has given rise to many well-adapted domestic races, and which through the aid of natural selection would equally well give rise by graduated steps to natural races or species. The final result will generally have been, as already explained, an advance, but in some few cases a retrogression, an organisation. Mr. Mivart is further inclined to believe, and some naturalists agree with him, that new species manifest themselves with suddenness and by modifications appearing at once. For instance, he supposes that the differences between the extinct three-toed hipparion and the horse arose suddenly. He thinks it difficult to believe that the wing of a bird was developed in any other way than by a completely sudden modification of a marked and important kind, and apparently he would extend the same view to the wings of bats and pterodactyls. This conclusion, which implies great breaks of discontinuity in the series, appears to me improbable in the highest degree. Everyone who believes in slow and gradual evolution will of course admit that specific changes may have been as abrupt and as great as any single variation which we meet with under nature or even under domestication. But as species are more variable when domesticated or cultivated than under their natural conditions, it is not probable that such great and abrupt variations have often occurred under nature, as are known occasionally to arise under domestication. Of these latter variations, several may be attributed to reversion, and the characters which thus reappear were, it is probable, in many cases at first gained in a gradual manner. A still greater number must be called monstrosities, such as six-fingered men, porcupine men, Ancon sheep, Niata cattle, etc., and as they are widely different in character from natural species, they throw very little light on our subject. Excluding such cases of abrupt variations, the few which remain would at best constitute, if found in a state of nature, doubtful species, closely related to their parental types. My reasons for doubting whether natural species have changed as abruptly as have occasionally domestic races, and for entirely disbelieving that they have changed in the wonderful manner indicated by Mr. Mivart, are as follows. According to our experience, abrupt and strongly marked variations occur in our domesticated productions, singly and at rather long intervals of time. If such occurred under nature, they would be liable, as formerly explained, to be lost by accidental causes of destruction and by subsequent intercrossing; and so it is known to be under domestication, unless abrupt variations of this kind are specially preserved and separated by the care of man. Hence, in order that a new species should suddenly appear in the manner supposed by Mr. Mivart, it is almost necessary to believe, in opposition to all analogy, that several wonderfully changed individuals appeared simultaneously within the same district. This difficulty, as in the case of unconscious selection by man, is avoided on the theory of gradual evolution, through the preservation of a large number of individuals which varied more or less in any favourable direction, and of the destruction of a large number which varied in the opposite manner. That many species have been evolved in an extremely gradual manner, there can hardly be a doubt. The species, and even the genera of many large natural families, are so closely allied together that it is difficult to distinguish not a few of them. On every continent, in proceeding from north to south, from lowland to upland, etc., we meet with a host of closely related or representative species, as we are likely to do on certain distinct continents, which we have reason to believe were formerly connected. But in making these and the following remarks, I am compelled to allude to subjects hereinafter to be discussed. Look at the many outlying islands round a continent, and see how many of their inhabitants can be raised only to the rank of doubtful species. So it is that if we look to past times and compare the species which have just passed away with those still living within the same areas, or if we compare the fossil species embedded in the substages of the same geological formation, it is indeed manifest that multitudes of species are related in the closest manner to other species that still exist or have lately existed, and it will hardly be maintained that such species have been developed in an abrupt or sudden manner. Nor should it be forgotten, when we look to the special parts of allied species instead of to distinct species, that numerous and wonderfully fine gradations can be traced, connecting together widely different structures. Many large groups of facts are intelligible only on the principle that species have been evolved by very small steps. For instance, the fact that the species included in the larger genera are more closely related to each other and present a greater number of varieties than do the species in the smaller genera. The former are also grouped in little clusters, like varieties around species, and they present other analogies with varieties, as was shown in our second chapter. On this same principle we can understand how it is that specific characters are more variable than generic characters, and how the parts which are developed in an extraordinary degree or manner are more variable than other parts of the same species. Many analogous facts, all pointing in the same direction, could be added. Although many species have almost certainly been produced by steps not greater than those separating fine varieties, yet it may be maintained that some have been developed in a different and abrupt manner. Such an admission, however, ought not to be made without strong evidence being assigned. The vague and in some respects false analogies, as they have been shown to be by Mr. Chauncey Wright, which have been advanced in favour of this view, such as the sudden crystallization of inorganic substances, or the falling of a faceted spheroid from one facet to another, hardly deserve consideration. One class of facts, however, namely the sudden appearance of new and distinct forms of life in our geological formations, supports at first sight the belief in abrupt development. But the value of this evidence depends almost entirely on the perfection of the geological record in relation to periods remote in the history of the world. If the record is as fragmentary as many geologists strenuously assert, there is nothing strange in new forms appearing as if suddenly developed. Unless we admit transformations as prodigious as those advocated by Mr. Mivart, such as the sudden development of the wings of birds or bats, or the sudden conversion of a Hyperion into a horse, hardly any light is thrown by the belief in abrupt modifications on the deficiency of connecting links in our geological formations. But against the belief in such abrupt changes, embryology enters a strong protest. It is notorious that the wings of bats and birds, and the legs of horses or other quadrupeds, are indistinguishable at an early embryonic period, and they become differentiated by insensibly fine steps. Embryological resemblances of all kinds can be accounted for, as we shall hereafter see, by the progenitors of our existing species having varied after early youth, and having transmitted their newly acquired characters to their offspring at a corresponding age. The embryo is thus left almost unaffected, and serves as a record of the past condition of the species. Hence it is that existing species, during the early stages of their development, so often resemble ancient and extinct forms belonging to the same class. On this view of the meaning of embryological resemblances, and indeed on any view, it is incredible that an animal should have undergone such momentous and abrupt transformations as those above indicated, and yet should not bear even a trace in its embryonic condition of any sudden modification, every detail in its structure being developed by insensibly fine steps. He who believes that some ancient form was transformed suddenly through an internal force or tendency into, for instance, one furnished with wings, will be almost compelled to assume, in opposition to all analogy, that many individuals varied simultaneously. It cannot be denied that such abrupt and great changes of structure are widely different from those which most species apparently have undergone. He will further be compelled to believe that many structures beautifully adapted to all the other parts of the same creature and to the surrounding conditions have been suddenly produced, and of such complex and wonderful co-adaptations he will not be able to assign a shadow of an explanation. He will be forced to admit that these great and sudden transformations have left no trace of their action on the embryo. To admit all this is, as it seems to me, to enter into the realms of miracle, and to leave those of science. So ends Chapter 7, Miscellaneous Objections to the Theory of Natural Selection.